Okay, so I propose we start, and I would like to introduce the speaker. So it's really my pleasure to have Dr. Adrian Chapman from University of Oxford to give these two lectures about graph-theoretical approach to Free-Fermion solvability. Yeah, and Adrian, the floor is yours.
Thank you. Yeah, it's my pleasure as well, and thanks very much for accommodating our time difference, everyone who is able to make it here this early. So my work is primarily on mathematical physics and in principle, or in particular, the application of combinatorics to condensed matter systems. So today I'm going to be talking about a graph-theoretic approach to Free-Fermion solvability. And so maybe just I'll start by saying, no, I'm going to try to write. Okay, yeah. So I plan to talk about right now, I'll first draw what I call a graphical outline. So today I plan to speak about essentially one of two topics. So the first topic, which will be in this lecture, is on generalizations of the Jordan-Wigner transform using combinatorics. And what we'll see is that sort of this set of generalizations coincides with a particular graph-theoretic class, which I'll describe in a second. And in the second lecture, I plan to talk about another sort of graph-theoretic class, which overlaps the first, but not completely, to which the Free-Fermion model originally proposed by Paul Femley falls. That's my plan for the second lecture. As I said, the first class sort of coincides with what are called line graphs. And the second coincides with what are called even whole claw-free graphs. And so it's sort of my hope today to sort of give a pedagogical introduction to the theory and build a theoretical framework from the foundation, and hopefully convince you by the end of these two lectures that we have a strong candidate for a class that includes both of these. And so that's what we're currently working on at the moment. And maybe I'll just sort of give a summary or a motivation for why there should be a class like this. And I'll tell you what the class is at some point. But for now, let's just leave that open. And if this is something you're already familiar with, I don't know that this will be too surprising, but so that's where we plan to go. And I should also note that there is some intersection between these two classes, as we'll see. So the references that I sort of plan to be covering, this is not by any means an exhaustive list, but the first sort of two important the two references from which I'll be drawing most of the material are papers by myself and my collaborators, Stephen Flamia and Samuel Ellman, who we did this work when the three of us were at the University of Sydney. And then sort of the inspiring papers for these works, the first is a paper called Anions in an Exactly Solvable Model and Beyond by Alexei Taev. And the second is a paper by Paul Femley called Free-Fermions in Disguise. And so just sort of as maybe a more rigorous outline for what I plan to be speaking about. So I'll talk about the Jordan-Wigner transformation, just to give kind of an introduction. And what a Free-Fermion model is, give some background on what I consider the setting for Free-Fermion models in this work. The second thing I'll talk about is sort of more of a deep dive into the graph theory. And finally, I hope to speak about transfer matrices, the transfer matrix method for solving these systems, and how it seems to have an interesting connection to graph theory as well. And then if there's further time, we can go through some examples. That's essentially what I plan to talk about. And as I said, this is not an exhaustive list by any means, but certainly if there are any questions, I can almost certainly find a paper that covers any questions. And finally, I just want to say that so the mathematical topics that I'll sort of assume a little bit of knowledge of are sort of basic graph theory. And some linear algebra, including the linear algebra of anti-symmetric matrices. And in particular, their characteristic polynomials. So okay. So the setting that I'll be speaking about is that of many-body qubit Hamiltonians. So everything that I'll be assuming is sort of finite and discrete. And so I'm in the Hamiltonian framework, and this is a Hamiltonian of n spins, n spin 1/2 particles, qubits, which I describe this way: some j on terms which are Pauli matrices, elements of the n qubit Pauli group. And I'll often also refer to these as just Hamiltonian terms with where I absorb the coupling constant b sub j into the definition of the term as well. So b sub j is a real number. And as I said, sigma sub j is an element of the n qubit Pauli group. And the sort of single qubit Paulis, maybe just for completeness, I'll just give the commutation relations to single qubit Paulis. Sort of usual relations. And also the sort of one-sided multiplication relation, x times y times z is the identity. Right. And as an implication of this commutation relation, this is the anti-commutator. All the Pauli square to the identity. And so generally we want the properties of the Hamiltonian H. So this includes things like the spectrum of H, the eigenvalues, and the correlation functions. Which these are not independent, but generally these are the kinds of things we want. And from these, you can go on to say calculate phase transitions or critical exponents and other interesting properties of the Hamiltonian from which you can sort of glean the physical behavior. And so yeah, so there's some other ones maybe we want, but generally we are interested in, I guess, solving the sort of many body properties of H. Okay, so now I'm going to speak about a special subset of Hamiltonians called Pre-Fermion models. I'm going to define these sort of generally. So a free fermion, an application of a free fermion model is sort of like a method for understanding certain properties of the spectrum. So it's a guarantee on the spectral structure of the Hamiltonian. So consider the fact that every Hamiltonian has a particular diagonal form. Right. All right, so generally in the diagonal basis, we can write H as a sum of Pauli Z up to some coupling constants. So you have the single body terms without loss of generality. You then have two body terms, and then the most general form of this is that you have L degree L terms. But a free fermion model is one such that only the single body terms actually survive or contribute. And when this is exact, this is an exact expression. Model. We refer to these indices as labeling what we call the modes, the free fermion modes. And these coefficients are what we call the single particle energies.
Excuse me.
Mm-hmm.
So I'm wondering here, so basically the idea is to kind of find the basis where the Hamiltonian is in the diagonal form.
That's right.
So basically the difficulty is to kind of find a way to transform, let's say, the previous all-to-all coupling Hamiltonian to this nice form, I guess.
That's right. So
okay.
Every Hamiltonian, every spin Hamiltonian has at least this form. But it may be the case that these higher order terms are, if not zero, at least very small. So this is at least a good approximation in some basis. But right, we'll be interested in the exact case. So in the case where all of the higher order taus beyond degree 1 are vanishing. And right, that's right. So that's right. So this is in just in some basis, not necessarily the basis that you're given. So you're given the Hamiltonian written in some basis, in the physical basis, the basis sort of dictated by the local constraints maybe of your experiment, but we want to transform it into a form like this, and this gives us quite a lot of information. Good.
Sorry, but in this case, is there a constraint that we have to work with, let's say, qubit or work with poly matrices? Because in principle, I can imagine that I have a local Hilbert space larger than 2, where this model is still free fermionic, right?
That's right. Yeah. So actually, right. So in some sense, almost every model looks kind of like a free fermion one over some subspace. And actually, so we're going to, I'll just mention that we're going to look more generally at models that are free fermion over symmetric subspaces. So the Hamiltonian won't look like this sort of globally, won't look like this globally, but will look like this over, say, like a particular symmetric restriction of the Hamiltonian. The symmetries are something that you can kind of gain from the physics. You understand what they are just by kind of looking at the model.
Okay, thanks.
Yeah. Right, because I guess I understand what I think you're getting at is that probably these higher order terms, you can think of them as being like sort of single body spins as well, but with the extra constraint that say like, you know, two of the low order terms multiply to a high degree one. And you can think of it that way, but generally there will be exponentially many spins if you do that in this basis. But for like an n-qubit model here, for this model, for the n-qubit case, you can have at most n modes, I guess, or n single particle modes, and that sort of tightly constrains the model. So you have basically n numbers from which 2 to the n energies can be extracted. If that's good, then right. In fact, I'll just write down what I said. So the spectrum of these models looks like, say, E sub x, where x is a binary vector of length n. So if there's n qubits in the model, then it's a binary vector. Sorry, then an n bit vector, I should say. Right, so just to jot down a few things, right, as I said, this is kind of a classical paramagnet in the eigenbasis. And as a result, you can kind of see that this doesn't generate entanglement between its single particle modes, because between eigenmodes, I should say. So its eigenstates are in some sense product states in the basis, in the eigenbasis of the Hamiltonian. And right, and then also the single particle energies, so like I need n single particle energies to reconstruct the entire spectrum. And that's a really nice compression. And I'll just say one more thing, which is that we will look at models of actually a general form, a more general form. Generalized case. Where H has this form. I want to say it says a bit string y, so y is some bit string. And the number of bits is, let's just call them big L for now. And for each bit string, we have a different free fermion spectrum. Y here is a projector onto an eigen space of a particular symmetry group. And we generally know what the operators, which are the sort of effective Pauli operators, the stabilizers of the symmetry group given by Y, are. And what this is basically saying is that the Hamiltonian over each sort of free fermion sector, so Y and Z operate on different Hilbert spaces, different local Hilbert spaces. So actually I can say this is actually, I should say this is a tensor product. And over each symmetry sector, once I specify that, then the Hamiltonian looks like a free fermion Hamiltonian. And so you can maybe see that actually, like, even just if I'm given the Hamiltonian and if I could get its exact spectrum, it's not obvious to look and see that the spectrum has this form, because what you're going to see is that the spectrum is a union of free fermion spectra, and sort of pulling those apart makes it less obvious to tell, you know, the task of pulling the free fermion spectra apart makes it less obvious to tell, like, exactly in what sense it's a free fermion model. And I guess another thing I should say is that over some scale, pretty much every Hamiltonian has this form. So, I mean, what I could obviously do is restrict to 2x2 subspaces, and then, you know, up to a trace term, then the Hamiltonian is going to basically be the sum of two single particle energies, the sum and difference of two single particle energies over that subspace. But so this is quite general, actually. But we're going to see that the symmetries and the sort of fermion matter terms, these are like the fermion part, and this is the symmetry part. Right, it's the sort of interesting, I guess, richness about these models is how these tend to look in local bases and sort of local physical bases. So in principle, they can look like anything, but the models we're going to consider basically allow us to do this decomposition and recognize exactly what each part of them look like. Okay. So then the next thing I want to talk about, just to give, I guess, sort of ground up view, is the Jordan-Wigner transformation. So just as an example, let's look at sort of the transverse field Ising model, which is one of the models that the Jordan-Wigner transformation is sort of famous for being able to solve. And I'm going to consider on open boundary conditions for now, and return to the case where the boundary conditions are periodic. Please let me know if my writing is too small. So, right, so sort of physically, this Hamiltonian looks like this. So if I have, say, n spins, I have an XX type interaction over each pair of spins, each nearest neighbor pair. And a Z local transverse field is sort of generated by Z, by field in the Z direction. And so we're going to perform an exact solution on this model. And the way we do this, perhaps this is familiar, is to define what are called Majorana modes. So the meaning of this Z term here, this Z factor, is that on the spins, I define, extending to the left in this case, a string of sort of Z operators. And that's going to define an operator that I call gamma. And so depending on whether the index on gamma is even or odd, the operator that I define on the rightmost spin is going to be either X or Y. And then the index, whether it's the, I guess the jth odd number tells me that there's an X on the jth spin, or if it's the jth even number tells me it's a Y on the jth spin. So these are how I define the Majorana modes. They satisfy what are called the canonical anti-commutation relations. And this implies, by the way, that the gammas all square to the identity. And they're also Hermitian. So typically, this is also solved in terms of ladder operators, which are like complex fermions. But I'm going to, for the time being, stick to the Hermitian case. Stick to the Hermitian case, and possibly return to the ladder operator picture momentarily. But what I just want to point out is that this canonical anti-commutation relation is very important. And you'll notice that it looks, exactly the same as the commutation relation between qubits. So the way you can think about these is that they are their commutation relations sort of generalize the commutation relations of the qubits. The qubits, a single qubit spin, I should say, single qubit operators, generate the group SU2 under exponentiation, and that's a double cover of the group SO3, right? So it turns out that the quadratics in the Majorana operators generate the group they generate a cover of the group SO2n. Yeah, a double cover of it. And that's a group called spin2n. And right, so that's, I think, all I want to say about this for now. But right, essentially, like, you can think about these as sort of having a geometric picture, which is that they sort of resemble a generalization of generators of three-dimensional rotations. And that generalization is to arbitrary dimensional rotations. And formally, that's the group, the orthogonal group, SO on a 2n dimensional space. And so under this transformation, the Hamiltonian is mapped to the following. So hopefully I have gotten the right phases. And so in the Majorana picture, the way you can think about this is it looks like every spin sort of contains two Majorana modes. Right, so we started with n qubits, and this transformation maps us to n spins, or sorry, to 2n Majorana modes, generating the group SO2n. And the couplings are also quadratic in the Majorana modes. And this first term couples an even spin and an odd spin of one index higher. So that has a coefficient of 1. And the second term just couples an odd mode and a mode of one index higher as well. So that's just this basically occurring within sort of the same spin block. And then this continues. And so we can write this Hamiltonian now as a quadratic acting a quadratic in the Majorana modes. And so what this looks like is, you can think of this as being a column vector, or I should say a row vector. To say there's an equivalent column vector over here of a Hamiltonian, which is the Hamiltonian of coupling coefficients. Right. So this is an anti-symmetric matrix. And the reason for that is that these Majorana modes anti-commute with each other. So the only non-vanishing contribution to the Hamiltonian is the coefficient, is the anti-symmetric part of the coefficient tensor. And so you'll notice that we have sort of an alternating pattern of 1 J. So the one term is the sort of inter-spin coupling term, and then the J is within the same spin, the transverse field coupling. And we have a factor of a half because each sort of off-diagonal part counts, the off-diagonal parts double count the same term. So you have to add a factor of a half to account for that. And so sort of compactly, this is written as H is minus ion 2. I designate gamma as a vector, as a column vector, then its transpose contracts on the single particle transition, or a single particle Hamiltonian, right? And so I'll just say this is called the single particle Hamiltonian. And that's also what defines this coefficient matrix, little h. So the reason I'm going through this so, I guess, methodically is what we want to see is actually like where we want to understand, I think, the meaning of this identification. So when I say that I set these Paulis equal to these gamma operators, we're going to actually generalize that notion. So so we're sort of trying to keep track of exactly what it is that we're doing when we do a free fermion solution this way. So once you have this, then you'll note that because of the anti-commutation relations, the canonical anti-commutation relations, which I wrote above, if you conjugate a Majorana operator by the Hamiltonian, the time evolution generated by the Hamiltonian, due to the canonical anti-commutation relations, this stays a single factor of the Majorana operators. The Majorana operators transform covariantly under rotation by the Hamiltonian. And so the single particle sort of rotation matrix is an exponential matrix exponential of the single particle Hamiltonian given by indexed by mu and nu. So I evolve by some operator mu, and I end up with a linear combination of Majorana operators nu with amplitudes given by the single particle rotation matrix, e to the 4ht. And then also here you can see that because H is an anti-symmetric matrix, an anti-symmetric real matrix, exponential is an orthogonal matrix. So these are rotated according to orthogonal matrices. And it turns out that's also exactly what's needed to preserve the canonical anti-commutation relations. So when I conjugate both of these by a rotation matrix, because they both transform covariantly, what will happen is I'll basically be conjugating an identity by an orthogonal matrix. I'll have U transpose returning the identity, so that preserves that delta function. Right, so and this is again implied by the fact that the Hamiltonian commutator with a single mode is actually -4. This factor of -4 is coming from the various sort of combinatorics of H, the single particle transition matrix acting on the vector of Majorana modes. Okay, so now that I know that I can do sort of these covariant rotations, I can essentially find that the diagonalizing orthogonal matrix of the single particle Hamiltonian H. And for any anti-symmetric matrix, you can always find an orthogonal matrix that brings it not to diagonal form, but to Williamson or block diagonal form. And so let me decide that I call my diagonalizing orthogonal matrix W, conjugate H by that. And this gives me a block diagonal form where its Williamson eigenvalues are off diagonal entries. So this is a block diagonal anti-symmetric matrix. And the only sort of parameters that are free here are the off diagonal values. And so then we're essentially going to take the logarithm of the matrix W. So I'm going to say that W, the big W, is e to the 4 times little w, and hopefully that's legible. And then by simply conjugating H by the same exponential, but for little w, now defined with respect to the Majorana modes as the coefficient matrix of Majorana modes. This gives something like.
Sorry, shouldn't there be a transpose on the vector gamma?
Yeah. Thank you.
Okay, thanks.
Thank you. And I believe I need a factor 2. Sorry, that factor confused me for a minute. So, right. So you end up with a conjugating orthogonal matrix on the single particle Hamiltonian. And so this gives you this block diagonal form when I plug in W for the orthogonal matrix. And then I can then write this as, I believe, minus I times the sum which I then define, well, going backwards through the Jordan-Wigner transformation, I get this. So, right. So by conjugating the Hamiltonian by the Free-Fermion generating, by conjugating the Hamiltonian by this Free-Fermion operator, I end up conjugating the single particle transition matrix, or the single particle Hamiltonian, by the single particle transition matrix of that exponential. And that brings me to block diagonal form for the single particle transition matrix. When you expand that out, you get this sum of now sort of paired off quadratics, so they no longer sort of interact beyond just being paired with sort of their monogamous partner. And under the Jordan-Wigner transformation, going backwards, this 2j minus 1 2j operator you'll see is actually just zj. So just multiplying these two gives me zj times I. And this is exactly the form of the spectrum that we wanted. So right, so what this essentially shows is that anytime I can find a set of, I guess, effective modes or some notion of a fermion under which the Hamiltonian can be mapped to a quadratic in the free fermion modes. I can then algebraically construct a diagonalizing unitary, which brings the Hamiltonian to diagonal form. And in fact, the diagonal form also has the property that it's a classical paramagnet in the diagonal basis. Now there's a few more things I want to note. So this start equation basically says that the eigenvalues of H can only come in complex pairs, complex conjugate pairs. Plus minus I lambda. And this unitary that I can use to diagonalize H, which is the exponential of an anti-Fermion operator, is efficiently sort of describable in terms of this little w, which is a 2n by 2n matrix. And then the other thing that we sort of want to make sure of is that the diagonalizing unitary has a well-defined spin description. So and the reason for that is that, so while I've said that e to the, gamma conjugating or gamma contracting the matrix W, can be found in terms of the Majorana mode, it may not be obvious actually how to go back, in what's to come, it may not be obvious exactly how to go back into the spin picture for this object. So this is actually given to us in this case by the fact the Majorana mode gamma are defined, are completely defined in terms of the Paulis. So if I have any pair gamma j, gamma k, then multiplying them gives me just some Pauli. It may be really non-local, so it may just be a string of Paulis that is of order the size of the entire system. But nevertheless, I can find what that is. And then in order to actually find the eigenstates in the original physical basis, I can just say, the eigenstate corresponding to E sub x. So I believe that's going to be the where x is the bit string in the computational basis. I believe this actually has a -9. Okay, so right, so this is now a well-defined sort of exponential of Pauli operators, and it's acting on a computational basis state. So this defines for me the eigenstate of the Hamiltonian in the spin picture. Okay, so I guess that's an example of a free fermion system. I just have a question. So are we, do we want to take a break halfway through?
As you wish. I mean, it's up to you, I guess.
Okay, I mean, if people are okay to continue, then I'm also fine to continue, but
yeah, we can continue, I guess. Yeah, we can continue, and I mean, just finish whenever you feel like. I guess it's all fine.
Okay. So right, so basically the question that we have is when is it possible to do this? So this is a really nice sort of solution. the workhorse method for solving one-dimensional systems. And we want to find sort of the most general case that we can for solving systems this way. Okay, so what do we actually need for this method to work? So we first need to find essentially quadratic pairs, I guess you could say, gamma j, gamma k, to assign to the Pauli terms of the Hamiltonian. Say sigma u, such that the commutation relations are preserved. Right, because in order to get here, we needed to say that whatever the quadratic gamma j, gamma k does to the gammas in the Majorana picture, the sort of spin version of that needs to also do the same thing to the spin version of operators in the spin picture. So essentially, we need to find these pairs that can reproduce the commutation relations. And what are those commutation relations? So so operators gamma j and gamma k only commute or anti-commute. Or sorry, gamma j, gamma k pairs only anti-commute if the size of the set, or sorry, the intersection of jk with say lm, so sorry, gamma j, gamma k, and gamma l, gamma m, if the size of that intersection is 1. So to have a common mode, then that mode will anti-commute with the other mode in the other pair. And if they don't overlap, or if they're the same operator, then they commute. So only if they share precisely one mode do they anti-commute. So the question that we have is, how do we find these pairs? Can be stated sort of purely combinatorially. So this question is sort of purely combinatorial. When can we assign pairs of modes to the Hamiltonian terms such that the Hamiltonian terms only anti-commute if the modes we assigned share one, have the pairs share one mode in common. And so to that end, I'm going to define something to keep track of the commutation relations of the Hamiltonian. And this is what we call the frustration graph. So commutation relations. Right. So this is defined as a graph, G of H, defined as a set of vertices and connected by edges. And V vertices is the set of non-zero Pauli terms in H. And I guess I want to give an edge condition. So a pair of terms UV is in the edge set. In other words, they're neighboring. If sigma U and sigma V anti-commute. So this captures the network of anti-commutation relations between terms in the Hamiltonian. And we can just look at a quick example. Oh, actually, I want to add a page to below us. So let me do that really quick. Okay. So for example, let's look at the XY model in a transverse field on 4 qubits. So frustration graph, note that frustration graph forgets about the coupling coefficients in front of the Hamiltonian terms. Periodic boundary conditions. So this will be my YY interaction. I guess we'll draw a circle for the XX interaction. And then each interaction will also have a local transverse field. So let me just change colors quickly. Each interaction type corresponds to a vertex on the graph. So in this case, there are 8. And then in this case also, so Z anti-commutes with X and Y, which also anti-commute with each other. And I'll draw this more cleanly in a second. And that's sort of symmetric everywhere. And this gives frustration graph as I'd like to bring this closer. Right. So each of these is an interaction, and their edges represent anti-commutivity. And the other thing I want to say is that, so note that this graph resembles sort of the 1D structure of the original model, but with some microscopic differences. So, right, it has this sort of 1D periodic structure, but on a small scale, it's sort of the detailed structure of the model that's going to be important. So the sort of main theorem of the paper that the first paper I spoke of is that this combinatorial question has an answer in terms of the frustration graph, and it's that the Free-Fermion solvability is possible if G of H is a line graph. Right. let me go down and define what I mean. Oh, sorry, still here. Right, so a line graph is a graph that is derived from the edges of another graph. And so let me just write down its formal definition. A line graph L of R has vertex set suggestively called E and edge set now called F. The graph is a line graph of the graph R called the root graph, if the vertices of L of R correspond to the edges of R, and the vertices are neighboring if in L of R, if corresponding edges are incident. So E of F, E and F are in the edge set of L of R big F, if E and F are incident edges in the root graph. Right, so let's look at this solvable model here. So as an example, we can say, let's suppose we have 8 vertices. The edges of this graph are shown in red. And if I map to the line graph, this is R. If I map to the line graph of R, then we see that each sort of red vertex is neighboring each red vertex in the original graph R, which corresponds to the edges of R, I should say, is incident to 2 other red edges at each blue vertex. So I wanted to do this actually. Right, so what this shows is that the 1D-XY Hamiltonian with transverse field frustration graph is the line graph of something. It's the line graph of this graph. And what's sort of important is, so that, as we said, is an indicator that the Hamiltonian has a Free-Fermion solvable, has a Free-Fermion solution. So in other words, in this case, G of H, frustration graph of the Hamiltonian, is the line graph L of R of some root graph. And then the important sort of, I guess, detail behind this is that not every graph is the line graph of something. So is a line graph, I should say. Okay.
Excuse me.
Hmm?
Yeah, so here it seems like this kind of way of constructing line graphs are a little bit like a duality somehow, right? Because you're
Yeah,
taking
so
like a graph and then just get the dual of it or something like this.
Right. So there are a few, I mean, I think that's a good way of looking at it. There are a few important things to know, which I guess I'll probably go into, but so the line graph of the line graph is not the original graph. So that's something that's it's not an invertible map. It is not its own inverse, or it's not an involution. There are cases where the line graph returns the original graph, in which case the line graph of line graph is the original graph, because so is the line graph.
Yeah, I guess in that case, it really kind of implies some duality, some kind of dualities, right?
Right. So I guess so. Yeah, you can, I guess, sort of think about this as, I tend to think of this as kind of the geometric picture. So on the left is sort of what we think of as being the physical space, or the real geometry on which, in this case, on which the fermions are hopping. So I said Free-Fermion solvability is possible if G of H is a line graph. It turns out that the root graph is kind of the geometry, or the sites on which the fermions hop. And then I guess it's sort of dual to the frustration picture, which is kind of the picture of what's happening in Hilbert space, which measurements or which directions in Hilbert space which will disturb the other ones.
Yeah. Okay. I see. Yeah. Thanks a lot. Yeah.
You're welcome. So I want to maybe go a little bit more into the graph theory and talk about some characterizations of line graphs. So the first characterization, which is probably the maybe for our purposes the most easy to see, is given in 1943. So this is by a paper by an author called Krauss in 1943. And so what this says is that a given graph is a line graph for some r equals v e. If the edge is in E, can be partitioned into non-empty, possibly empty although they can only belong to at most one empty one, clicks such that every vertex belongs to exactly 2 clicks. Right. So let me pull down this figure. Oops, I want orange. So what this means is that, right, we can group the edges of this graph into complete graphs, into complete subgraphs, or sets of edges which induce complete subgraphs. And for this case, we see that if I group them this way, then every vertex belongs to two triangles, one orange and one blue triangle, except for the ones at the end here, which belongs to just the orange triangle. So the ones at the end, you have to choose the empty click as the sort of other click that the vertex belongs to. And so when you can do this such that every vertex belongs to exactly two clicks, possibly being empty, then the graph is a line graph. And to see that, we can see that the vertices in R are mapped to clicks under the line graph mapping. So right, if I say I have some edges incident at a vertex. Here's my vertex in R, and the edges are shown in blue are incident to that vertex in the center. Then under the line graph mapping, these four edges are mapped to four vertices in the line graph, and these are all mutually neighboring. This is the vertex in R. This is a click in L of R. And clicks will be important for us later on. So the other thing I want to mention is that cycles in R are mapped to induced cycles or holes. And let's see. So what I first want to do is say, suppose we have a 3 cycle, and its edges are all incident to each other. So this is both a click and a cycle. And under the line graph mapping, it's mapped back onto itself, actually. So for cycle graphs, this is a general property. Every cycle is mapped onto a cycle under the line graph mapping. But because this graph is called K3, because K3 is both a click and a cycle, we add another new page. We can also arrive at this same graph, the K3 graph, via a line graph mapping on 3 edges incident to a single vertex. So this also maps to K3. And this is called K13, or the claw. And it turns out this is the only time this happens. So the only time the root graph R is not unique if the graph you're given is a line graph. And so there's lots of sort of interesting examples for small graphs. And I think it's important to show that there are places where I think finding free-fermion solutions looks confusing, and the reason is actually precisely because of these kinds of ambiguities. So, what this is saying is essentially if I have a single qubit whose Pauli operators all mutually anti-commute, so if I had, say, X, Y, and Z here, then there are sort of two ways I can find a free fermion solution to the single qubit Hamiltonian. I can either give every operator in X, Y, and Z a pair of modes such that they all share a single common mode, or I can sort of each give them 2 out of 3 of a common triple of modes. It's interesting because this sort of ambiguity is actually remarked upon in one of the papers at the beginning that I mentioned by Kitaev. So he gives a single qubit free fermion solution to a model in that paper called the Kitaev honeycomb model, which I can talk about. And sort of interestingly, he remarks that there's actually, so he does this qubit by qubit, and he remarks that there's 2 sort of ways to find a free fermion mapping for each individual qubit, and it's precisely these 2. So maybe just what this is sort of saying, or what I'm sort of saying, is that if you happen to be in the setting where the frustration graph is a line graph, then the way you find the free fermion solution is you assign a Majorana mode to each click in this decomposition. And then what will happen is Hamiltonian terms sharing the same click will now also share a Majorana mode, and so they'll be guaranteed to anti-commute. So vertices sharing click will anti-commute. Okay.
Excuse me.
Mm-hmm.
Now you consider the graphs on the plane or 2 dimensions?
No, these are arbitrary, but they do need to be finite.
Right. Can we consider the graphs in higher dimensions?
Yes.
Yeah. Okay. Then in that case, what is the holes? What is the holes of the graphs in higher dimensions?
So a hole is an induced cycle.
Cycle.
It's a cycle through which there are no.
Cycle is in that case that, for example, the triangle is a cycle.
Right.
Triangle is a cycle, but in higher dimensions.
Oh, are you thinking of? Sorry, do you mean like a simplex?
Uh-huh.
So, well, this particular graph, you can see has 6 edges. It will be mapped to the octahedral graph. But when I say a hole, what I mean, so I can actually try to draw it, but when I say a hole, what I mean is sort of in the graph-theoretic sense. So a hole is a cycle where every vertex in that cycle has precisely 2 neighbors in the cycle, so no other neighbors. So like what I mean by that is, maybe a good way to see that is through this example. So I'm going to it's just a 4 cycle, but I cut through it with an edge. And this will map to, so this edge is incident to every vertex in the 4 cycle. So the 4 cycle itself is mapped to another 4 cycle. And then the extra edge is mapped to a vertex that neighbors every vertex in the original 4 cycle. So when I say a hole, what I mean is like, yeah, let me draw what I'm calling the hole. So it's a subset of vertices such the only neighbors in the subset form a cycle. So there's no edges that go, you know, even though these blue edges form a cycle, there's no edges that go like that. Yeah, so this right, because these original 4 vertices don't form a hole because there's this white edge cutting through cutting through it. But now that edge is a vertex, and if I pull that vertex out, I still have a cycle. Right, so this is called a hole or an induced cycle.
Okay. Yeah, I
Great
understand.
question, thank you.
Okay. Thanks.
So the next characterization I want to talk about is what's called a forbidden subgraph characterization. So I drew these ahead of time to avoid having to draw them right now. But this is given by Benecke in 1970. And it's the forbidden subgraph. So it turns out that there are precisely nine graphs, which constitute sort of forbidden induced subgraphs of line graphs. So if any subset, what I should say is that if any subset of vertices induces one of the graphs above, the full graph is not a line graph. So you can think of these as kind of local obstructions to the free fermion solvability of the model. So even though, right, there might be some way that I can try to find a clique decomposition of the graph sort of everywhere, but I end up sort of, you know, maybe one of these graphs is just somewhere at one spot as an induced subgraph of the graph I started from, then I don't have a line graph. So I'm always going to sort of like run into a frustrated situation in that case. And so
sorry,
maybe you can.
Is this like an exhaustive list, or there might be more?
No, there aren't. So there are equivalent characterizations when you're given certain promises about the graph. So I believe when the graph has degree at least 7, the number of forbidden induced subgraphs can be reduced to 3. But so there's 3 other forbidden induced subgraphs, but this is the most general one. So this is every single forbidden induced subgraph. There's only 9 of them, and they have size at most 6 vertices, and that's all there is. So maybe the reason that's so, okay, I guess that's not obvious, but the reason it might not be so surprising is that you can see that, like, so the way I might try to enumerate through these things is say, okay, well, maybe I recognize that a claw is a forbidden induced subgraph, and we'll just see how that works in a second. But maybe I recognize that a claw is a forbidden induced subgraph. Then now I need to sort of consider of the remaining graphs to find new forbidden induced subgraphs, only claw-free graphs. So I just, now, once I know this is forbidden, I can start kind of looking through claw-free graphs and try to find sort of forbidden induced subgraphs within those that are also forbidden subgraphs. And now, again, it's not obvious that this list should be finite, but in this case, it is. And what it sort of is showing is that you only kind of need to go out so far before you're guaranteed to sort of, before your sort of obstruction will show itself, I guess. And so, yeah, I think that's pretty surprising. I agree. But again, the other thing is that a generally like non-line graph, a general non-line graph can contain, say, like claws all over the place. So like, for example, a cube graph, every vertex is the center of a claw. So, so that's really, sorry, that's a very bad drawing, but right. So if every vertex is the center of a claw, then essentially you have to remove quite a few vertices before it becomes claw-free. And I guess would be 4, but I don't know off the top of my head. And so, okay, so a few of these actually sort of we can maybe just see immediately as to why they should be forbidden. So, for example, for the claw, so those graphs are sort of special. They're called claw-free graphs. Talk about these further. But what this is sort of saying, or what this is reflecting, I should say, is the fact that no two edges can be incident to a third edge. Sorry, no three edges. No three edges can be incident to a fourth edge without being incident to each other, without at least two of them being incident to each other. So let's see, right. So suppose I draw something like this, and I have, well, I can put another edge here without loss of generality. Maybe I put another edge not incident to this first one. So I'll call this one blue. So I don't want any pair of blue edges to be incident to each other. But now there's nowhere for me to put the third edge because either place that I put it, it's going to be incident to one of the original two. So therefore, these graphs must be claw-free. And the other sort of maybe useful one to look at would be this middle column, top row. I'll just copy it. And so this one maybe sort of reflects a way that is you become frustrated when you try to do the click decomposition. So suppose I try to group the edges of this graph into clicks. I might start with this just to kind of play around, might start with this one. So now the topmost vertex here has to belong to the other. So this has to be part of the partition. But then let's do red. So now this triangle, in order to satisfy this vertex belonging to exactly 2, has to be part of the partition. But now there's nowhere for me to go for this remaining vertex because if I try to include these 2 green, well, these don't form a click because they're 2 edges that or rather I should say this middle edge would have to belong to 2 clicks, and that's not a partition, so that's not allowed. And in fact, no matter how I try to do this, I'm going to run into some frustration like that. So it's clear that this is not a line graph. And if an induced subgraph of a graph is not a line graph, then the global graph is not a line graph. So essentially, that's what these other sort of these other 8 graphs besides the claw here are reflecting. You know, you see a lot of back-to-back triangles essentially because these are places where it's impossible for me to you know, perform this decomposition or this partitioning without running into some vertex that you know, whose incident edges don't form a click somewhere. Okay, so I just want to mention one caveat, a couple caveats to this. So this is a good place to actually have this image. So so the first set of caveats I want to talk about are called twin vertices. So twin vertices have the same neighborhood. And sort of called in literature, I believe, true twins are vertices with that property that are neighboring. I don't think I've got this mixed up, but and false twins are non-neighboring. So this graph is a good example because let me just paste in a fresh copy of it actually. So, right. So it has both true and false twins. So even if I did mess up the names, it's okay because this graph contains both. So what I would call the false twins are this pair of red vertices, and then this pair of blue vertices are going to be true twins. So why are these important? So suppose that I call the red vertices J and K, then the Hamiltonian term sigma J times sigma K is a symmetry. So the product, whatever the neighbors to say J are, K has those same neighbors. So sigma J times sigma K commutes with every term in the Hamiltonian and therefore commutes with the entire Hamiltonian. We can restrict to a symmetry sector of J times K, mapping that to say plus or minus 1, allows us to essentially remove one of the 2 vertices. So I can replace J with K up to a scale factor by restricting onto a symmetric subspace of the product. So that's for what I called false twins. If I have true twins, which are neighboring, then the product, rather the exponential of sigma L times sigma M is a unitary. Oh, these are non-neighboring, so this has to be that e to the sigma L times sigma M, let me erase it, is a unitary mapping sigma L plus sigma M to essentially sigma L or sigma M up to coefficients. So I just find whatever the angle I need to rotate sigma L plus sigma M, some linear combination of them, into one of the other of the two. And this gives me a basis by which I can remove one of them. And so if I can remove one of them, then now this graph is now a line graph. And so in the former case, I do a projection onto a symmetric subspace to remove one of them, and that gives this graph. And so that is a line graph. And it's the line graph of, I believe, this graph. Doing fly, I believe it's that. Right, and then if I remove the neighboring twins, then that gives me a cycle, which is also a line graph. This was the blue case, and this is the red case. Sorry, I've reversed that. This is the red case. This is the red vertex here. This is the blue case. Doesn't matter which one I pick, but it works. So these constitute symmetries, kind of graphical symmetries of these forbidden subgraphs. And if essentially they are wired together into the global graph such that you can sort of still remove them, if they're still twins like this, then you can sort of restrict onto either a symmetric subspace or find a local rotation that removes them for you. And so sometimes there are ways around this. Okay. Right. Okay. So then the other thing I want to talk about is what are called graphical symmetries. So these are symmetries that always come with a Hamiltonian that satisfies this property. And they essentially correspond to the more generalized version of a Free-Fermion solvable model that I mentioned before. So what I'll just say is that as a Z2 matrix, the adjacency matrix of the graph A sub G, sorry, I should say A sub L of R, the line graph, satisfies the following decomposition. That's the transpose, where the matrix B is 1 if, Bij, the matrix element of B is 1 if the edge I is incident to vertex J. So this is a edge to vertex incidence matrix. And it's 0 otherwise. So what essentially this matrix contraction is doing, this factorization is doing, is it's counting mod 2 the number of vertices where a pair of edges could be incident, and any pair of edges can be incident at most one vertex. So if those vertices are incident, if those edges are incident at a vertex, and this is 1 and otherwise it's 0, which is to say that this contraction is the matrix element IK of the line graph. And so why is that useful? Well, products of Hamiltonian terms can be thought of as Z2 vectors. So I'll say that sigma of a vector v now with a vector superscript is the product of vertices in the vertex set with the Pauli raised to the exponent v sub j, where again, yeah, v is a z2 vector. And these are Hamiltonian terms. So I guess I would say that this is sorry, I think I want to say that this is the edge set. And so then what that means is that A dot V, the adjacency matrix dotted into this vector, tells us the terms that sigma V anti-commutes with. And furthermore, if I have a V for which A dot V is 0, then that means that there's a Pauli symmetry of the Hamiltonian. So Pauli symmetry is given by right. So and we plug in our factorization, and what this implies is that the symmetries are either of one of two forms. So B transpose dot V is 0 itself, or that's case 1, or B dot B transpose, I guess what I should say is that B transpose of V is in the kernel of B. Okay, so what's in the kernel of B transpose itself? So B transpose has a row index given by a vertex and a column index given by an edge. So if that's 0, what that means is that this is a subset of edges such that every vertex is incident to even many of those edges. So every vertex incident to even many edges in, I guess, the subset labeled by V. And then, so what 2 is saying is that, the kernel of V, I should say, so every element of every column of V is the vertices it is the pair of vertices, I believe, to which an edge belongs. Sorry, every row is the set of vertices belonging to a given edge. So in order to, right, so what's in the kernel of V is the all ones vector, which is to say that every edge contains 2 vertices. And so the only vector in the kernel of V is the all ones vector. So this is the all ones vector. And this means that every vertex is incident to odd many edges. In case 2. So case 1 naturally corresponds to cycles because any even degree subgraph can be partitioned into cycles, the edge sets can. And case 2 sort of corresponds naturally to the parity symmetry operator. So this is the operator such that when I take its Free-Fermionization, when I take the Free-Fermion mapping of the product of Hamiltonian terms, Majorana modes cancel out such that a single mode is left at every vertex. And so that gives me the product of all Majorana modes. And so that's the operator that is canonically called the parity operator. Right, so let's just quickly revisit our example to see what this looks like. So I'm just going to pull an example from the previous slide. Sorry if this is dizzying. And I'm also going to grab the graph. This example. The root graph, I should say. So case 1 corresponds to the terms, say, going around this cycle. So all the red vertices, the edges incident to the cycle. Let's make that explicit. So that's this collection of edges in green. And that's the product of all the XY parts. So, right, that's X1, X2, Y, X3, X4, Y2, 3, and Y1, Y4. And that is possibly epiphases, but I don't think so. Z1, Z2, Z3, Z4. That's the green product. The orange product, which I will label in orange, is a subset of edges where every vertex is incident to odd many edges. In fact, every vertex is incident to exactly one edge, and this is actually a perfect matching of the graph. So in this case, it's maybe just a little easier to see what that product is because that's all the Z terms multiplied. And so that product is Z1, Z2, Z3, Z4. And we see from this example that sometimes these symmetries can actually coincide. So what that means is that there's some, I guess, redundancy in the way that we specify the symmetry sectors of the model. So once I specify, say, an eigenvalue of this cycle symmetry, I've also specified an eigenvalue of the parity of the parity symmetry. So this is a parity, and this is a cycle. And we can keep track of which eigenvalue is assigned in the Free-Fermion mapping by giving a sign to the Free-Fermion term. So the mapping is defined up to the exchange say gamma jk with gamma k gamma j, because all I required of this mapping was that the commutation relations be preserved. But if I'm allowed to switch, so switching the order of these operators just changes the sign of that term, and that doesn't change the commutation relations. So I'm in general allowed to do this. And what this looks like, for example, in the cycle case. So what we need to do is assign an orientation to every edge of the graph. And let's just pick an orientation. So I'm going to pick one. And the way that I'm going to associate a sign to my Free-Fermion term given by the orientation is by saying that the sign will correspond to a plus sign if the arrow is directed upward in the label. So if it's directed, say, 1 to 2, that's a plus sign. And if it's directed downward, so say 3 to 1, that's a minus sign. And it doesn't matter actually which one that I do, I believe. So, well, what I mean to say is that this ordering, while this depends on the choice of labeling of my mode, what actually matters is going to be the orientation of the cycle itself. So that is to say whether the cycle is even or oddly oriented. Let's recalculate the green product. And so under my Free-Fermion mapping, 1, 2 is mapped to I, x1, x2. It's a mapped to I, gamma 1, gamma 2. Oh, sorry, I think in the original picture, this was gamma 1, gamma 3, so let's say that. And this is going down actually, so this has a minus sign. So gamma 1, gamma 3. This times x3, x4. Which is
2, 4, I guess.
2, 4, right? So I, gamma 2, gamma 4, it's going up. Then y2, y3, which here was the, all right. No, I believe I made the first term actually is wrong. So, oh no, that's right. Sorry, thank you. You're right. This is 2, 4. So that's minus I. The arrow goes down. So it's gamma 2, gamma 4. Y2, Y3. Oh, it's confusing because I've labeled the modes, right? So the modes are not the same as the edges. So I'm going to say that this is let's make this the 1, 2 edge. So that's going up. It's I, gamma 1, gamma 2, and then the other one must be gamma 3, gamma 4 going down. Right. So these 1 cancel out, and there's 3 modes between them, so that contributes to minus sign. After canceling those, the 2 have a mode between them, the one that's left over, so that contributes another minus sign. Then the 3 cancel, and then the 4 also cancel. So we end up with a +1 overall from the commutation relation, the phase from the commutation relation. And then we have minus I, minus I, minus I, gives I, and then plus I gives -1. So the value of this product is -1. And so this is chosen by choosing an orientation on every edge in the graph. And so since these operators are the same, in this case, the cycle and parity operator is the same, choosing the -1 orientation restricts us to the -1 eigenspace of parity. And so, right, so what I should say is that for a graph with M edges and vertices and C components, there are M minus N plus C independent in terms of the independent cycle symmetries. So as edge subsets, that's how many independent cycle symmetries you have. So this is the number cycle symmetries. You can have at most 1 parity symmetry as well, because there's at most 1 way to I guess, take the product of all the Majorana modes. If there's even many Majorana modes, you can do this. And if there's odd modes, you can't. And the other important thing is that given an eigenvalue, configuration for the cycles, you can always choose an orientation that works. That satisfies that. Mm-hmm.
Yeah, sorry, could you explain again what is component here? I'm a bit lost.
Oh, sorry. So this graph, I've implicitly assumed up to this point that this graph is connected. And of course, like, that's a very natural thing to assume, because if my Hamiltonian frustration graph has many different disconnected components, then that's essentially a sum of commuting collections of terms.
Sure.
But if it has C components, you have to add a C for each, a cycle for each component. So for a single connected graph, this C is 1, and that's generally the case we care about.
Perfect. Yeah.
Right. So I can say maybe one more thing, but it looks like sort of at the 2-hour mark. So if fine, I'll just actually just leave that topic, which was transfer matrices, which is maybe more relevant to next time. And then I'll just add a page to kind of summarize what I've talked about in this lecture. So in this lecture, gives generalized Jordan-Wigner transformations. And then the solution, or the solution criteria, if the frustration graph is a line graph, you always get a set of symmetries. Which are cycles and parity, depending on the graph and depending on the representation of the graph as well. These symmetries can sort of form different groups. And then the other important thing that I mentioned is the forbidden subgraph characterization. And so that'll be important for my next lecture. And then, of course, the other characterizations for when a graph is a line graph. So maybe just in the last minute, I just want to touch on, these are just pictures, but so this is the original XY model in a transverse field. This is the most general 1D XY model we have. Nearest neighbor X, XY, YX, and YY terms. Shown in the sort of colored clicks is the click decomposition of this graph. So they decompose into 5 clicks. Every vertex shares one of these shares a pair of these 5 clicks. And they kind of alternate in this like geometrically alternating structure in 1D. So yeah, they sort of are joined. There's sort of partitioned into 2 upper and lower clicks on the red sort of black unit cell, and then on the green blue unit cell, they are partitioned in sort of like, I don't know, east-west clicks. And then so shown here is the root graph. Yes, there was a question about 2D models or higher dimensional models. So this is the type honeycomb model, the compass model on the honeycomb lattice with bonds which are directionally dependent on the direction of the bond in the graph. So all incident edges in the honeycomb Hamiltonian anti-commute. And so we can partition that into triangles. And it turns out that, again, the root graph of this model is actually the honeycomb graph itself. So yeah, this model was one of the first models we looked at in this work. It's sort of interesting that, in fact, the root graph of the model is also the interaction graph of the model. It was, there's a recent proposal to use these for error correction. And so this is an example of a subsystem error correcting code in 3D, where around every space, there's a product of x's and a product of z's included among, I guess, what we've been calling the Hamiltonian terms. And these anti-commute along 1D chains. So the blue operators, the blue faces here, anti-commute in sort of 1D XY alternating fashion. And so this is a model that was proposed, I believe, by Preskel, Joachim O'Connor, Roberts, and oh no, I'm forgetting the last name, but this is called the frustrated hexagonal 3D color code. And so, right, so they anti-commute in these 1D chains, and then the 1D chains themselves commute with each other. And then finally, here's a model that we introduced, we call it the Sierpinski-Hanoi model. So it has 3 local terms defined on the sort of filled cells of the Sierpinski gasket. And it turns out that the frustration graph is what's called the frustration graph is the line graph of a graph called the Hanoi graph, which is a graph representing transitions between states of the towers of Hanoi problem. And so you can calculate, this is an exact spectrum of this model at finite size from the you sort of like at this size. And we also added a local transverse field. So as we vary the transverse field, we see that the model's single particle energies kind of diverge, and there's 2 avoided crossing points. And so what we sort of found numerically is that these 2 avoided crossing points approach 0 as we increase the system size. And so we expect that these sort of correspond to scale invariance in the infinite limit. Right, so let's go back up. Leave my summary slide on the screen. Yeah, so that's all I had today. And if take any questions, and I thank you very much.
Yeah, thank you very much. Okay, is there any other questions? I mean, I'm really impressed, and so far I don't have any specific questions, but yeah, thanks again, Adrian, and maybe we continue again on Friday.
Yeah, okay, right. All right, thank you.
Yeah, thanks a lot for staying up late for for lectures. Yeah.
No problem.
Yeah, have a nice evening. Yeah.
Have a good day. See you later.
See you.